Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun, and in today's presentation, we will be talking about neural network. Even before I demonstrate practically how neural network works, I request you to subscribe to my channel and share the videos with your friends and relatives. To build a neural network model, I will be using the data set which is called as drug treatment. Let me access this particular data set in SPSS. I will click on the file menu, choose the option recently used data, and SPSS shows 10 different files which I had mostly used recently. The very first file that you can see here is drugs. So let me just click on this particular file. This is a very useful data set. It helps us demonstrate a lot of analysis. What is this data set all about? I have got 7 variables in this data set, and the sample size in this data set is 200. So I have got 200 patients' information about 7 different parameters. What are some of the details that we know? We know the patient's age. What is the sodium concentration in his or her blood sample? What is the potassium concentration in the blood? The patient's gender is given. The BP level is given. Cholesterol level information is given. And this is a derived variable which I have created by taking a simple ratio of sodium concentration in the blood and potassium concentration in the blood. So by dividing 0.79 by 0.03, I'm obtaining the number 25.35. And the last variable is very important because this variable talks about which drug did the first patient respond to. So these 200 patients suffered from a common illness, and when we administered the drug Y to the first person, this particular person was able to respond to drug Y. So if we have to interpret the first record here, the first record here is for a female. Her age is 23 years old. The sodium concentration in her blood is 0.79 and the potassium concentration is 0.03. She has high BP level, high cholesterol, and she responded to drug Y. The second person responded to drug C, third person responded to drug C, and the fourth person responded to drug X. We will be today talking about a supervised learning technique called as neural network. There are many advantages of using a neural network. One main feature of neural network is that it is very robust to noisy data. I repeat, it is very robust to noisy data. Secondly, it can handle nonlinear patterns in the data. If there is a linear pattern, I might as well use a linear regression model. But when the data becomes very complex and there is a lot of noise in the data, I can't use it within linear regression. So I move on to other techniques, and one such popular technique, which is widely considered as a gold standard when it comes to modeling nonlinear patterns, is neural network. Neural network can also handle extremely complex data. It is a non-parametric approach, so there are no distributional assumptions behind the data. So these are all some of the advantages of neural network. It is widely used in image processing. It is used in text classification. It is used in banking sector, and there are other areas as well where a neural network finds a lot of application. What are some of the disadvantages of neural network? The main disadvantage is that it takes longer training time as compared to some of the other models. Secondly, neural network works like a black box. With this approach, you will be able to get your predictions, you will be able to get your charts, you will be able to implement it in a real-time scenario. But there is not a single equation that I can get saying that this is the equation of a neural network, and with this equation you will be able to estimate. And finally, neural network is less interpretable as compared to some of the other models like a decision tree model. So these are the three disadvantages of a neural network model. What I intend to do in this video is to use drug of response as the dependent variable. And I am also going to use the patient's demographic details and previous medical history to predict for which drug is a patient most likely to respond to. Once I know that patients are most likely to respond to a particular kind of drug, in future, when a new patient comes to me, I can note down his profile, and based on his profile, I can recommend the best drug that he can take so that he recovers from the illness soon. So with this being the background, let me proceed to build a neural network model. SPSS offers two different types of neural network model. I will click on the Analyze menu, and as you scroll down, you can see the neural network option. In SPSS 15.0 and any version prior to 15.0, you might not see the neural network option being present. This version came into picture only from SPSS 16.0. Now, within neural network, there are two options. The first option here is what is called as MLP, or multi-layer perceptron. And the second one is what is called as RBF, or radial basis function. I will choose the second function, which is radial basis function. So the canvas on the left-hand side, SPSS displays all the variables that you can use to model your data. And to the right side, you can see SPSS is expecting me to specify a dependent variable, a factor variable, and a covariate. Dependent variable can be scale or it can be categorical. In my case, I will be using the variable drug as the dependent variable. When it comes to factor, I will choose certain variables like gender, BP level, and cholesterol, and push this along the factor list. Finally, I have the covariates. I can choose the two scale variables, namely age and the ratio of sodium to potassium content in the patient's blood sample. We can standardize the variables, and this is very, very important because when the variables are measured in different units, say, for example, age is measured in years, and if you had a variable like height, it would be measured in feet. Years and feet cannot be compared. So there is a possibility that variables with larger numbers will be assigned higher weight. So it's always a good practice, maybe for segmentation techniques or maybe for neural network and such algorithms, to always standardize the covariates. When it comes to these settings, I've chosen the dependent variable, I have chosen the factors and the covariates. I will not be choosing sodium concentration and potassium concentration because I have anyway derived a new variable called as Na_K, which is nothing but the ratio of sodium concentration to the potassium concentration in the blood sample of a patient. Let me move on to the partitions option. And as you can see here, I'm going with the default option, that is 70% will be used to train the model and the remaining 30% will be used to test the model. We can change this ratio if we want to. However, I will not be disturbing this setting as of now. When it comes to architecture, there are a lot of things that you can do. You can have several hidden layers, or you can go with just one hidden layer. When a neural network has only one hidden layer, it is called as a shallow network. On the other hand, when you have multiple hidden layers, it becomes what is called as deep network. I'm not going to disturb the architecture as of now. Let me click on output. There are a couple of useful options that you can click here. One is what is called as ROC. This is used to study the network performance. ROC stands for Receiver Operating Characteristic Curve. Using this graph, we can understand how well the neural network model has performed. We can also choose the lift chart if you want to. I will not be choosing the lift chart. I will ignore it for time being. There's another useful option here, which is about independent variable importance analysis. out of the 5 variables that I have taken, I want to know which is the variable which mostly drives the patient's choice to respond to a particular drug. So to understand which variable drives response to a particular drug, we can use the independent variables important list. Finally, I can choose to save the predicted category as well as the predicted probability of the dependent variable. I will ignore exporting the model as an XML file, and there are certain other options as well, like how you treat for missing values. Here, I will go with the default option of exclude. And once these things are ready, you are all set to build your neural network model. So let me just click on OK. SPSS very quickly produces the neural network model. There is a bit of case summary here. As you can see here, the neural network model, out of the 200 samples that we had, 138 has been used for training, which is roughly around 69% of the samples have been used for training, and 62 cases have been assigned for testing. So we are testing for 31% of the cases. SPSS also lists certain other information like how many factors did I use, gender, BP level, cholesterol, how many covariates. There are 2 covariates here, age and NA_K. What are the number of, how many units did we specify? So SPSS has used 9 different units here. And when it comes to a rescaling method, we are using the standardized option here. There's also another concept which is called as the activation function. You can see here, there is the first layer. This is the input layer. The second layer is the hidden layer. And the third layer is the output layer. And when it comes to the hidden layer, we have used 10 units. And SPSS has used the activation function, which is called as softmax activation function. When it comes to the output layer, again, we are using the activation function, and that activation function is an identity activation function, and the number of units here is 5. The error function that we have used for this particular neural network is sum of squares. There are other error functions as well, but for the purpose of this demonstration, I would like to keep it very, very simple, and I've chosen sum of squares. Let me scroll down. You can see the neural network model that is used at the backend. The first layer is what is called as the input layer. All the input variables like gender, BP level, and cholesterol, I have pushed it into the input layer. Then we are processing the input layer to find out certain weights, and based on the weights, we push it into the activation function and take out the results. And then we are able to predict in the output layer which drug does a patient respond to, right? So you can see here the output layer consists of 5 different levels of drug, and this is the hidden layer. It's a bit difficult to interpret the neural network just by looking at the neural network model, but this is a simple layer which is called this is a simple neural network model which is called as a shallow network. We call this as a shallow network because there's only one hidden layer. If you had multiple hidden layers, you would call this as a deep network. So this is the input layer, the first layer, and the second layer is called as a hidden layer, and the third layer is what is called as the output layer. Let me scroll down here to look at the model summary here. Now, when we look at the training error, percentage of incorrect predictions were 5%, which means that in the training, we have been able to obtain around 95% accuracy. 95% is a good number. When it comes to testing, if you look at percentage of incorrect predictions, it is 17. So, which means that roughly 83% of the cases have been correctly predicted. But there is some kind of a gap between the training error and the testing error, and this is almost 12%, which indicates that the model suffers from the problem of overfitting. We don't want to see a big gap here. 5% and 17%, there's a big gap. It's a clear indication that the model may suffer from the problem of overfitting, which is a topic of discussion for another video. Here, let me just proceed with the interpretation of the output. Now, what can you say looking at the classification model, or sometimes it's also called as the confusion matrix? You can see here, SPSS gives you two different tables. The first one is for the training sample and the second one is for the test sample. In the training sample, if you look at the percentage of correct classification, this is very useful. In the row, what you have is the actual data, and in the column, you have the predicted category of response to a particular drug by the patient. Predicted by who? Predicted by the neural network model that we have built. So there are 5 types of drugs. And when it comes to predicting drug A and drug B, the neural network model is doing a very good job. It is 100% accurate in the training data set. Usually, we do not get such a high number. When you get such a high number, like 100%, it's a clear indication that the model is over predicting. So when it comes to drug A and drug B, the model is 100% accurate. When it comes to drug C, X, and Y, the model is 91%, 94%, and 93% accurate in the training data set. Now, let's just focus on the test data set. You can look at drug A, the performance of the model is only 60%. In the training data set, the model did a good job of predicting drug A to the extent of 100%. And here, the accuracy has collapsed drastically. It has come crashing down to 60%. So when it comes to drug A, the model is clearly suffering from the problem of overfitting. Drug B is 100%. Drug C is 100%, drug X is 87%, and drug Y is 83%. So we have a problem in our hand, which is the problem of overfitting. Usually the model, if it is 80% plus accurate, it is a good model, but we would like to see consistent results between the training and test. If the model is accurate between the training and test, if the model is giving us consistent results, then we can go ahead and say the model is generalizable. If the model is not generalizable, it means that there is a clear problem of overfitting. Let me look at some of the other outputs. What you see here is called as a ROC curve, or receiver operating characteristic curve. It's a visual index of the performance of the model. Now you can see here in the y-axis, we are taking sensitivity, and in the x-axis, we are taking 1 minus specificity. And the 45-degree line here is the reference line. Farther the line from the reference line, more accurate it is. And nearer the line, as compared to the reference line, it means that less accurate is the model. Now, the different colors correspond to each of the drugs, and it is sort of not very clear because each of these lines here is very close to the vertical axis. Now, to have a better display, what I will do is I will double click on the ROC curve. I will select the y-axis. Now, once I choose the y-axis, what I can do is I can just right click and then click on the very first option, which is called as properties window. A new dialog box comes up. Here, I can choose the option scale. And when it comes to minimum, I will choose the option 0.9 and then say apply. You can see here the lines basically come away from the vertical line, but the display is still very poor. So what I'll do is I will now choose the vertical axis. Now, once I choose the vertical axis, here when it comes to maximum, what I will do is I will choose the number 0.1 and then click on apply. Now you can see here, this graph is more interpretable as compared to the graph at the background, because our ROC lines were almost merged with the vertical axis. Let me just click on close. Let me again close this window. So this is how the ROC curve appears. Now, what is the rule of thumb? Farther the line from the 45-degree line, more accurate the model is. Nearer the line to the reference line, less accurate the model is. Now, our first impression when I look at this particular graph is, let's look at the legend here. The blue line corresponds to drug A, and then you have drug B, then you have drug C, which is shown in a green line, then you have a drug X, and finally the yellow line is drug Y. Now, drug Y seems to be least accurate, whereas the blue line, that is drug A, seems to be most accurate. When you look at the green line, that is drug C also is giving you high percentage of accuracy, which means that our model is doing a good job of classifying drug C as well as drug B. It is not doing such a good job of classifying drug Y. Now, this is your ROC curve. A better way of interpreting the same graph would be to just study the area under the curve. This is very, very important. This area under the curve is very important because the area under the curve lies between 0 and 1. If the area under the curve is close to 1, it means that the ROC curve is doing a good job. On the other hand, if the area is less than 0.5, we don't take such a category or such a classification seriously. Because if the area under the curve is less than 0.5, it means that randomly guessing is a lot better than a model. We don't want such a situation. We want our model to be outperforming a random guess. So here, when you look at the area under the curve, higher the value, better the accuracy. The highest number that I can see is 0.998. And 0.998 corresponds to drug A. Even drug C, it is 0.998. So it means that the model is doing a good job for drug A and drug C. Other numbers are also very, very high, which is a good sign. But the model has learned the characteristics of drug A and drug C very, very well. Remember, I said that when we compare the training and the test, we don't want to see too much of inconsistency, but that is what we have. There is some bit of inconsistency in the results between the training accuracy and the test accuracy, and therefore the overall classification output you need to take with a pinch of salt. Now, this is another important graph which I really want to draw your attention to, because it tells me the importance of each variable in predicting the response to a particular drug. As you can see here, this is the normalized importance. Let me just double click on the normalized importance and select the bar, right click, and then choose properties window. Let me now go to fill and border and change the color. I can choose this and simply say apply and then click on OK. So this is the normalized importance table. What does this tell me? Higher the importance, it means that its contribution in driving the dependent variable is very, very high. Hardly a surprise, because sodium to potassium ratio is found to be the best variable. It is found to be the most important variable which drives response to a particular drug. The second best variable is BP level. Third variable is age. The fourth variable is cholesterol. And here the last or the least important variable seems to be gender of a person. So the three most important variables would be sodium to potassium ratio, sodium to potassium, the ratio of sodium to potassium concentration in the patient's blood, and followed by BP level and age. These are the three most important variables which drive his or her response to a particular drug. So in this particular table, we have seen a lot of things here. We began by looking at the network information. Then we looked at the network diagram. We proceeded to interpret the model summary. Then we could see the classification table. We proceeded to look at ROC curve and then area under the curve. And finally, what we have is the independent variable importance. You can see here to what extent does a variable drive the dependent variable. That is what is being shown here by the independent variable importance. Many times the clients would use the feature importance graph to make further decisions. One other thing which I would like to show here is when I go back to the data set and scroll to the right side, if you remember, I had drug variable as the dependent variable. Now, what do I see? I see 6 new variables being created here. Now, these 6 variables, the first variable is the predicted value. And you can see here the neural network has predicted drug Y. What is the actual drug that the patient has responded to? Drug Y. And my neural network model, when I use a radial basis function, is also predicting the drug of response to be drug Y. So if there is consistency here, it's a good sign. It means that the model is doing a good job of classifying him. Look at the second variable, drug C and drug C, which is again a correct classification. 3 is also good, not bad at all, which means that the model is doing a good job of classifying drug C versus drug C. The top few cases, it appears that the model has done a good job, drug X versus drug X. Is there a misclassification? Please look at the 7th variable. The actual category, the actual drug to which a patient has responded to is drug Y, but the neural network here has misclassified the drug of response as drug X. Along with this, you see 5 pseudo probabilities being generated. These are the 5 pseudo probabilities. And when you look at each of these numbers, what happens here is that out of each of these 5 numbers that you see, the biggest number is this particular number corresponding to drug Y. Higher the pseudo probability, greater the chance that the record will go into that particular category. So here, out of all the 5 categories, you can see 1.023 being the highest, and therefore the first person has been classified as drug Y. When you look at the second row here, the biggest number is 0.841, which means that there is a higher propensity that the second patient responds to drug C, and therefore the model has predicted drug C as the predicted response. Look at the third one, 0.96 is the highest, and therefore the third record has been classified as drug C. So whichever column is the highest amongst these 5 columns, the patient will be assigned to that particular category. So with this, I have come to the end of today's presentation. In today's presentation, we have looked at neural network model. Specifically, we used radial basis function. We looked at different features in neural network. What are the advantages, disadvantages? What is the training accuracy? We compared it with the test accuracy. What is the feature importance score? We looked at the ROC curve. And we also looked at what is the predicted probability and predicted score. I thank you very much for watching today's presentation. I request you to hit the like button and subscribe to my channel and share my videos with your friends and relatives. Thank you very much. Have a great day.